So I'll keep it on for some time. Okay, so this is going to be very different from all the other presentations we've been having. Not focused on one particular content area of mathematics, but the discussion is supposed to be on problem solving. I wanted something like this because perhaps it's the central endeavor of all mathematics, but as such, we don't spend that much time thinking about this in its generality, and I thought we need an opportunity for that. I'm very fond of quoting something from Paul Halmos, where he asks, what is mathematics really about? What is it about? Oh, because I'm putting something like that and asking, of course I want you to say that, right? But otherwise, yeah. And so he really, sort of thinks a bit, he says, is it really about theorems? Like, for instance, fundamental theorem of algebra, a beautiful theorem. Or is it really about proofs? Some people say it's not really about theorems, it's about proofs. Proof of, Gödel's proof of incompleteness theorem, real tour de force. He quotes other people, he says, no, it's not really about, it's about formulas, Cauchy's formula, right? Very beautiful formula, okay. So, or is it about, no, not formulas, is it about definitions? Some people meaningfully say that mathematics is really about good definitions. Menger's definition of dimension is a classic. Well, because think of something like a dimension, how do you even define something like that, right? Okay, so, or is it about methods? Method of successive approximations, right? We just saw, very beautiful thing. Is it really about all these things? And then Halmos goes on to say, I'm paraphrasing, it's a couple of pages. It's a very beautiful piece of text as far as I am concerned, where he goes on to say that, look, mathematics is about all these things. But if you really pin down and ask, what is the raison d'etre of a mathematician? I mean, why do you exist as a mathematician? The answer is to solve problems. Problems of various kinds, where they come. In fact, you're less worried about where they come from, but if it's there, you want to solve it, right? So that is at the soul of mathematics, he says. And I think it's so if that is so, then what is this really about? And then for mathematics education, if you accept Halmos, I mean, if you don't, that's a different story altogether. Now, the goal of mathematics education, a very important goal should be to give this mathematical experience of problem solving, an attitude to problem solving. I would say perhaps the most important thing is creating an attitude to problem solving. What is that attitude? I mean, what is a healthy attitude to problem solving? First thing to say, no panic, right? No panic. And this is perhaps the biggest critique that we all keep coming to in mathematics education, because at the end of 10 years, 12 years, people come out with that tremendous sense of panic on facing problems. So perhaps I would say, so there are some things that I do want to say generally about problem solving. But before that, I mean, why talk about problem solving? Let's do a problem, right? Here is a problem. I just picked from somewhere. There are 6 towns. They're all in a flat land. The land is flat. And the distance between any two the smallest distance is some m kilometers. The largest distance is big M kilometers. Okay, so this is what you've got. There are some 6 towns given to you, and you are told that the shortest between any two is m, and the largest distance is uppercase M. Show that m by m is greater than root 3, greater than or equal to root 3. The distance, the ratio of the largest and shortest distances is at least root 3. This is what it says. You find a problem like this, how does one react to it? What is the kind of clues one can have? What is a helpful clue here? Flat land, right? Somebody goes out of the way to give a hint like that, right? Okay, so can one make use of that? Well, this suggests a clue. I'm just going to now do one exercise, how I would solve the problem. This is actually from, I think, Vladivostok Olympiad. This is how I found it. In fact, this is asked to me by one student who was trying to solve the problem. And, there are like many solutions, and here is one way of going about it. So, because it's flat land, let's consider two cases. One case is when no three are collinear. Say three of them are collinear. Collinear, do you put one L or two L? Whatever. Two L's, okay. So suppose three of them are collinear, right? Then what can I say? Let's call them A, B, C. Here is A, B, C is somewhere in between, right? Now, well, without loss of generality, C is somewhere in between. So let me say that, I don't know, C is here, right? What is this without loss of generality? Okay, I want to put C somewhere, so I put it in somewhere. So now I put it in such a way that AC by AB, what do we know about it? It's less than or equal to 2. Yeah? But what do we know about AC and AB? Little m is less than or equal to AC, and AB is less than or equal to m. Right? In this particular case, what do I know? In this particular case, is greater than or equal to 2, which is greater than root 3. AB by AC. I should have written AB by AC. Where is mine? Yeah. This is what I wanted after all. Yeah. So I want AB by AC greater than or equal to 2, which is the form in which I want. Yeah? This is correct, but yeah. The problem is that there are 6 towns, right? And the distance, if I look at the smallest distance between any two of the towns is m kilometers. The largest distance between any of the towns is some other uppercase m kilometers. Show that the ratio of m by m is greater than or equal to root 3. This is how the problem is given. Okay. Now, what is the first idealization I'm making? I'm thinking of towns as points, right? And assume that the land is flat. So I'm thinking of these m points. And now I'm saying, consider the case where 3 are collinear, then it's very easy for me to solve the problem. And that I'm saying is a helpful clue here. Okay. Why this particular case? This is what a hint or a clue is doing for me. I'll come to this kind of discussion later. But what about the other case? Now I think I can erase this email address. So no 3 are collinear. So case if no 3 are collinear, they are like scattered around like that. Now how do I picture this? There are these 6 points that are there, and I know that they are lying around. One way of imagining what is going on is to look at, consider the convex hull of the 6 points. I look at the convex hull of these points. Now, what can the convex hull be? It can be a triangle. It can be a quadrilateral. It can be a pentagon. It can be a hexagon. Right? That's all there is. Now, I'm just going to give you a solution and then discuss what is going on. That's my this thing. But this is different from. Now, somehow by playing around with these pictures that I have got, right? In the triangle, what is going to happen, right? In the case of quadrilateral, what's going to happen? Look at all these things. I have to somehow come up with some relation to this root 3. What is this root 3 doing for me? Right? Now, somehow the root 3 is another clue. I have to go from, I know that it has something to do with angles, right? This is another intuition that, especially I'm saying like your 13, 14-year-old is going to have this kind of clues in life, because at that time you're doing trigonometry, you're doing a lot of these things, some sine theta, cos theta, root 3 by 2 is a immediate flag, right? And that's how you think. And then
you say convex hull of 6 points,
yeah.
and triangle quadrilateral, you're taking points at a time. Because any three, they are not collinear, there are going to be triangles.
There will be triangles, but now I'm looking at
All the 6 points lying on a quadrilateral.
or no, all the 6 points will be inside. All the 6 points will be inside one such. I can always find one, right? That's all.
Okay, all 6 points will be
Inside a triangle, or it may be inside a quadrilateral, or inside a pentagon, or a hexagon, right? These are the different cases.
all 6 points.
Yeah? So, convex hull of all the 6 points, yeah? Is going to be one of these, right? In each of these cases, I have to do some argument. Yeah, I'm going to draw all of them. I'm going to draw all of them. Or, no, I'll draw each case. In the hexagon, what do we know? Now, can I draw a hexagon? I'm not sure at all, but I can. No, just a hexagon. So, the convex hull, suppose it looks like this. All these fellows are the 6 towns that I'm looking at, right, are all at the vertices of some hexagon, right? Think of a board on which you have represented these towns as pins, and you are taking a rubber band around it and putting it around. That will give you the convex hull. It doesn't matter where those 6 are, right? All I know is that they are not collinear. Any 3 are not collinear. That's all, right? So I can physically represent it that way. So this is one case. But what do we know about there is at least one interior angle greater than or equal to 120 degrees. Yeah, that's for sure. If I've got a hexagon, right? So I don't know, maybe this one is. So let me look at this triangle here, right? So I have a triangle here. Triangle with maximum angle greater than or equal to 120 degrees. Yeah? What about the triangle case? There are 2 extremes, right? If the convex hull is a triangle, that means D, E, F are sitting inside the triangle somewhere, right? Take any one of them. Let me say D. Our friend D is somewhere here. Then draw these, right? I know that all the towns are lying inside this triangle. Take any one of them, right? Let me call it D. What can I say about the angles here? There are 3 angles here. So what do I know? At least one of these angles is greater than or equal to, that's very nice. At least, so there exists a triangle here. Oh, I'm sorry to write, I'm used to writing like this. There exists a triangle with at least one angle, so I might as well write it as with maximum angle greater than or equal to 120 degrees. There are only 2 cases left. We can just examine those. And it's not going to be very difficult to see now, right? Because it's a quadrilateral. I'm sorry to draw quadrilaterals like this, but if the convex hull is a quadrilateral, I know that The vertices are A, B, C, D. Inside somewhere our friend E and F are sitting here. So let me take this diagonal and put E is going to be somewhere here. So consider this triangles. Apply the same argument as before, and I know that this is true. Let's move fast. What about a pentagon? Is this a pentagon? Yeah. Okay. Now we have one more town somewhere, F. Where is it? Let me call it here. Draw the lines from the vertices and again argue that there is one. That is true. So now I know that if these no three are collinear, there must be a triangle somewhere formed by these towns such that the maximum angle of this is at least 120 degrees. Now 120 degrees is good news because, some nice connections with root 3. So what is the picture we have got finally? So we have proved now so we have shown that in this case whatever that statement says is true. So let's call this triangle C A B and this let's say is greater than or equal to 120 degrees. Yeah? I know that there exists a triangle. I'm just calling it ABC with, I know that the max angle is greater than or equal to 120 degrees. Without loss of generality, I'm marking it here. So let me say this is C, this side is A, this side is B. Yeah? The opposite side to the angle, I'm naming them little c, A, B. I have to call it something. So what do we know about the relationship between C, A, B? There is something which, law of cosines, right? Law of cosines. Law of cosines tells you C squared is A squared plus B squared minus 2AB cos C. What is cos C? Now cos C, now C I know is at least 120 degrees. So cos C is minus half, less than or equal to minus half. Yeah? So what do I get? I get C squared is A squared plus B squared minus AB. Now I know that A must be less than B. Law of signs. C squared is greater than or equal to. C squared is greater than or equal to. Of course. Yeah? Plus AB, of course. See. I was thinking about this and I forgot. So now I know therefore C squared is greater than or equal to 3A squared. Yeah? So what do I know? C by A is greater than or equal to root 3. But I know that the largest distance was M. So M is greater than or equal to C and A is less than or equal to little m. M is less than or equal to little a. Sorry. So therefore, M by M greater than or equal to root 3. Now this is the next, let's just, is the idea clear? I'm sorry? So if C squared is greater than or equal to 3A squared, surely C by A is greater than or equal to root 3, right? Now C by A is already more than root 3. Now our big M is bigger than C, little m is smaller than A, therefore that ratio is going to be bigger than, I'm just saying that M by M is greater than or equal to C by A, therefore. Now this is an experience of problem solving, that's all I am talking about here. Now this is not really problem solving. I am giving a solution, you are listening to the solution and verifying that what I am saying is a solution. This is not problem solving. But already there is a tremendous educational value, in my opinion, in this. Of course, one major problem in this is what problem is this? Trigonometry problem? Geometry problem? Combinatorics problem? I don't know. Okay, that is not what I'm talking about. Okay, so these are the things I thought we can spend a few minutes thinking about. What I'm talking about as the mathematical experience that our student has, right? If problem solving is the soul of mathematics, what is the kind of problem solving experience, right, which I would call genuine mathematical experience that our children get, right? Now, can I take this off now? This particular way of doing, there is a lot to reflect on, what all we did, and I hope you will. I mean, I'm welcome to discuss these with me as well. I think there's a very nice solution. There are many mathematical processes that are employed in these, and those are what I want to think about. Now, as far as I can see, there are 3 roles for problem solving, right, for mathematics teaching. One is problem solving for teaching math. Two is teaching problem solving. 3 is teaching mathematics through problem solving. And all these 3 are very different. In some sense, what I want to talk about here, what I want us to think about, is that this is what we do. We do a lot of this. Unfortunately, much of what happens is this gets translated into end of chapter exercises. These are extremely important. End of chapter exercises are very, very important. I'm not denying. But that's one experience of problem solving. That's all. What is the role of end of chapter exercises? There is a certain mathematical content that is privileged. Okay? You know, there are some definitions that you must understand, right? There are some theorems that you must know, right? There are certain techniques that are famous, centuries we have developed, important ones. You must learn those techniques. Learn those and let me check whether you have learned it or not, right? I'm giving you certain content. Have you understood this content or not? Understood, I'm not even sure. Can you follow that in a slightly changed context? This is what I call end of chapter exercises. And what I'm trying to say is that especially in secondary, higher secondary school, primary at least, you know, with small children we are a bit more liberated. But in secondary, higher secondary school, almost 90% of problem solving experience for all our children is only these, if we are lucky. Maybe we are unlucky, it's probably somewhere in 99.99%. What about this? We don't do enough of this. In fact, if we consider problem solving as a central thing, I think we should teach problem solving. I don't think it's natural. I don't think so. I don't think you know, I've seen many people talk, and I don't believe this personally. I think it needs to be taught, it needs to be learned. It comes through exercise, it comes through lot of application of mind and habits, many. In particular, attitude to problem solving is there. How do you teach problem solving? Well, this is something you need to think about. There are, you know, great masters of problem solving like Polya, David Hilbert, you know, Newman, Arnold, you know, many mathematicians have given many, many nice suggestions and hints. Our own thing, there are great teachers like P.K. Srinivasan or A.R. Rao, people like who for primary level, elementary level have, you know, produced a lot of such material. But we need to go very, very far on this. How do you teach problem solving? I am not going to give a lecture on that. I mean, Polya is great. I can offer some suggestions from reading these. But we need to reflect on what kind of heuristics we use. How do you know, Polya says draw a picture. Always draw pictures. Do case analysis. Look at extreme cases. There are many, many processes that are involved. And I think those are things we need to think about. And the third, which is really what Polya is about, is really, can we teach mathematics through problem solving? In fact, he is almost fanatical about it. I was very lucky to have a professor in Bits Pilani who taught combinatorics an entire course using Polya's method because he was a student of Polya. And it's great fun because everything is through problems. Okay, so Polya has 4 categories of problems. I'll just mention before we move on to some more problems. MF problems, D problems, E problems, and DAD problems. MF problems are, every chapter is structured that way in what Polya. MF are motivation and forerunner problems. Problems that motivate you to look at what is coming. Forerunner gives you some taste of what is coming later. Then the second category are definitional problems. You never state definitions for, and say definition is sacred. Every definition that is given comes with a problem that changes the definition a little bit, so that you begin to see why it should be defined this way. Now, this is very important. In linear algebra, there is this mysterious thing that students learn at this level called determinant. Some very strange, mystic creature where you multiply this, change sign, and miraculously you get a number that carries all kinds of information, right? Why would you define something like this, right? So, his point is that you must routinely question definitions. Every definition must be questioned. And you need a few problems that help you question definitions, get you in the habit of questioning definitions, because if you accept definitions, then you are not really doing mathematics. That is his point. Third is exploration. Yesterday in the projects we talked about exploratory problems, and maybe we can talk more in whatever time we have. But the need for problems that are where the student actually explores. And then last, direct application and drill. That is the term he uses, and I love it because you need that. You need the drill, right? It's like physical exercise to keep in shape. Unfortunately for us, DAD problems are almost all that our books and our pedagogy offers. Huge amount of direct application and drill. Now, I see the necessity for all these things, especially in a mass examination pattern. It's very difficult to do all the rest. But somewhere if we accept that that's the only thing about mathematics, we are compromising way too much and somewhere missing the soul of what the mathematics experience should be about at all. Now, what can we do as individuals? Very little. But somewhere, as a profession, he was saying, we, right? In that sense of we that I'm talking about, somewhere we all have to, at some point, say that we have to change the role of problem solving. Now, if that is so, I think yesterday in Jonaki's talk, she was mentioning, the National Curriculum Framework and, what it says about the teaching of mathematics and so on. She kept quoting these. And one of the things that I would like to mention there is this shifting of focus from content to process. This is, talked about as one of the important things. I was personally involved in this exercise and a position paper on teaching of mathematics. Anybody who is interested, please write and I would be happy to send copies off. I think we should discuss many things there. One of the things that's talked about there is shifting of focus from content to process. Because the content areas of mathematics are very clear. Algebra, geometry, trigonometry, arithmetic, data handling. I think they have evolved through centuries of thought. So I don't think we need to perturb that too much. There's a lot of thought that has gone into this content areas. You can question many things about it, the pacing of it, which should be done earlier, later. But I think anybody who thinks seriously will admit that most of these are, very important parts of mathematics. But processes. What are processes in mathematics that children go through? Lots of processes. Let me just write a few and then get back to some problem solving to see how these processes are at work. Processes, I mean representation. Moving between multiple representations. Here, what did we do in this problem? A very simple thing. Represent a town as a point on a plane, right? Suddenly gives you some new way of thinking about it. But it also comes with abstraction. And something that we are not talking about here, but in other lectures, we talked a bit about approximation. It's a well-kept secret that for school mathematics that many solutions are approximate, right? estimation. I mean, these are, I think, very important mathematical skills. I doubt if you can do any decent science if you're not good at estimation and approximation. You can do very good mathematics, very likely, but chances are that you're out of science if you can't do these. Visualization. And then there are some things that are, to me, really unique to mathematics. Here is one. Generalizing to make a problem simpler. Many cases, particular cases are very difficult to solve. You generalize, you suddenly get some intuition. Now this is, I think, a very mathematical insight to me. Use of heuristics. This is perhaps the best kept secret in math education, that when you do mathematics, you use a lot of heuristics, which are not guaranteed to succeed always, but you know that very often it works, rules of thumb, and you try them. Searching for counterexamples. This is a very mathematical process. I would say actively searching for. If you have some making conjectures, arguing. I'm deliberately using the word argumentation here, not proof. Right? Proof comes much later. Building some intuitive argument. And making conjectures is extremely important, and searching for counterexamples to your own conjectures is perhaps the major act of humility that mathematics teaches you, perhaps. I think, in fact, it's only when you have looked very hard for counterexamples and you don't find any, you start developing some faith in what you're thinking of. So these are all, now this list goes on, right? I can give you more, and I think what is a good list, what is an essential list is something that's good to think about. But even in the little examples that we looked at, right? Look at some processes that are involved. Those processes that we made use of, used content knowledge, right? The law of cosines and law of sines we made critical use of. But in some sense, it is this idea that you abstract away, you represent it differently, draw pictures, try something, use analogy. These were actually very critical. And the role of hints that are, it's, otherwise you can talk all kinds of things about problem solving, but it's like throwing somebody into the water. Of course you will swim, right? But come on, you want to give hints, you want to give help. And so how is that? How does that go? And so another very important thing here is use of symmetry, invariances, searching for invariants, and these two are very closely related, but looking for invariants and formulating an invariant. Symmetry, using symmetry. Now, we can talk about most of these in an open-ended exploratory way, but we don't have that much time, and I don't want to go on with that. But so yesterday we were talking about projects where we were talking about problems that take much longer and one can do. And that's really where the payoff, if you want, is, in my opinion, not these short problems, but still, in this already we can do a lot. Right, so instead of listing more, let me just take a couple of more examples, and then we'll see what I mean. So here is a problem, one of these traditional problems, right? Show that x plus y to the p is less than x to the p plus y to the p for xy positive 0 less than p less than 1. Right? I'm now talking about something that I found in one of the textbooks. And here, I saw the solution and I was very impressed. So I thought I should tell you. But impressed for what reason? It says, without loss of generality, now here is a problem. Look at this problem. How would you solve this problem? How would you attempt? Where would you go? By induction. Okay. What other technique?
Induction P should be integral.
I never said anything about it. And I have put 0 less than P less than 1. So, binomial expansion, okay. Right. Now, we really don't have time. This is really what one should do, right? Take up something, spend time thinking about it. But also in a group of 70, 80 people, it's very hard to do collaborators stuff. But ideally in groups of 2 and 3, one must do it. Not individually. I think it's very important, right? Another major secret that is kept is that people think that mathematics is you sit and gaze at the navel and some, under a tree and wisdom comes. No, it comes by discussion, by talking, right? If children talk mathematics, I think there is no problem about fear of mathematics at all, right? It's not a private activity. So in 2 and 3, we can do it. But here,
This is like triangle inequality with other powers for P. So,
okay.
where would be triangle inequality?
Okay, so here we are now talking something, yeah. Okay. Now here, the power, I want to illustrate the power of what I mean by looking for invariance, symmetry, etc. Says without loss of generality, we can take this is a marvelous statement. Says, what do you mean WLG here? How can, this is not what he says, but it's certainly true. That is, if I consider the transformation x to tx, y to ty, t greater than 0, the inequality holds. So if I take this and transform it by scaling, the inequality holds anyway, right? So it doesn't matter. I can take x plus y to be 1. And if x plus y is 1, we are through because x and y are positive. So I know that x is less than 1. Therefore, x is less than x raised to the p. Y is less than 1. Therefore, y is less than y to the p. And you are through. Done in 1 minute. Now, somewhere, this is what I would call an aha moment. Okay, a small observation. The power of such techniques is what I am talking about as mathematical experience, right? The power of such observations that we can make. Now, when can such ideas strike? Well, when we see many such applications. We have to show many such applications, and then we can start seeing. So here is another, so I just want to take a couple of examples of invariance thing. And every single problem I'm talking about, by the way, comes from some source which is intended for students, school students, in fact, somewhere or the other. So here is one. Which problem? Okay. Yeah. Okay. So let me also talk about doing things like impossibility proofs. I think that's another experience that we should give our children. Lower bound arguments, impossibility proofs. Yesterday we were doing Sudoku estimates that I was talking about. Making estimates is very important, and here is another one. Okay, we have a whole lot of problems relating to ruler and compass construction, right? Straightedge and compass. Can you construct some particular geometric figure using only a straightedge and compass? Now, unfortunately, I think these are becoming old-fashioned and many people are not interested, but I think there's in terms of mathematical experience, I think there is a curiosity there for a logician, for sure. Why do you look at the straightedge and compass? Why not look at only straightedge? Okay. So I'm going to be very informal, but assure you that all this can be formalized if you wish. For instance, suppose I'm given a circle, right, and a point P outside it. Draw a tangent to the circle passing through P. Draw a tangent through P. Can you do this with a straightedge? Remember that you can't put it and start rotating. Rotations are not allowed. Then you're not using it as a straightedge. The answer is yes, and I'm not going to tell you the solution. Please try. It's nice. Here is the next question. In fact, there is a series of questions, and this is what I wanted to illustrate. Bisect a given line segment Yeah, it's a straight edge. So what can you do? You can just draw a line. Yeah, you can draw lines. You can draw lots of lines. You can draw lines, that's all. However long, right? Because these are arbitrarily. Yeah. Yeah, placement you can.
You're saying you cannot use a compass.
You cannot use a compass, yeah? That's the whole point, right? So bisect a given line segment using only a straight edge. Using only a given or whatever straight edge, yeah. These are all very old problems. I'm not saying anything new. These are all like, couple of centuries old problems, not. Yeah. So, what do you think?
By paper folding,
Sorry?
by paper folding we can do that.
Okay. Yeah, good. Now you're talking some. But in paper folding, unfortunately, it's not only a straight edge. There's all sorts of things happening. You're using a plane, right? There's not only one ruler. Okay? So, I agree, but that's a different thing. In fact, it's not, what you've got is not a one-dimensional object. Yeah? What do you think? How would you do it? Any idea? Forget it. I'm going to tell you, it's not possible. Question is, even if somebody tells you that no, it's not possible, how would you expect to prove it? Right? Here is an example of what I like, being a logician myself, a meta-mathematical argument. Okay, the argument goes as follows. And as I said, these are very old arguments. Suppose there is some procedure. It doesn't matter what it is. Given AB, it's going to find M. Hopefully, it's a midpoint. Right? Now, what I do is the following. Right? Because you've got a procedure, the procedure doesn't know the length of the line, right? The length of the line segment. It's going to do something. If it knew the length of the line segment, there is no question about midpoint. You can always compute it and tell you. It's supposed to measure, right? So you have no idea how long that thing is going to be. Now this is on a plane P. Come up with a bijection to a plane P prime such that it preserves lines but not midpoint. I'm saying given any plane P, right, construct another plane P prime and a bijective map which will take points on P to points on P prime such that any set of points that constitutes a line here will, if you take the image, the set of points constitute a line there, but whatever is a midpoint here is not a midpoint there. Can you construct such a bijection? Yes, but this is a clue I'm giving. You have to sit and do it. I'm not going to solve the problem. In fact, and it's not difficult at all. I assure you that you can actually do it. But this has a consequence for us. Why? Whatever procedure, whatever algorithm, whatever, super duper computer you can use, it doesn't matter. If it could solve the problem on P, right, it would apply the same algorithm, whatever it is doing on P prime as well, and it would announce the image of M as the midpoint on P prime, which it is not. And therefore, this is not possible. Now, in what I said, there is a huge amount to be formalized. But in fact, as I said, I assure you that it can be formalized to the satisfaction of logicians, which is a terrible thing to do, but it's possible. All this can be formalized. But the moment you go through all this, you learn so much. You learn so much because the payoff is enormous. You can show now that using only a straight edge, show that you can't find finding the center of a circle. Drawing a line that is perpendicular to given line segment. There are several more. Same thing here. You can take, once again now, you take your plane on which your circle is lying, choose a point outside the plane, right? And have a map that goes from one plane to another through this point, and set it up in such a way that it will translate circles to circles, but it will not preserve midpoint. And that's enough to show that you can't do this. So there is a whole lot of these things that you can do. Why am I saying it's the power of invariance that we are talking about? Now, this is what I mean by a certain skill that mathematics offers, which is unique to mathematics, and the kind of insights that you get is more, but let me just take one more example and stop. I have lots of examples, especially in the open-ended case, but here is, maybe since I put invariants, let me give you an example involving finding a good invariant. My entire aim is to say that we need a good collection of problems, solutions, methods of solution, approaches to problem solving, and classify them in some way by which what the method of solution teaches in terms of mathematical values, right? And if we can communicate that, make a habit of it, offer more problems, then I think it's very nice. So here is one. Oh, by the way, how did I forget? Every problem, one important thing is to not just talk about a problem, but also its extensions and generalizations, right? Without that, there is no problem solving at all. Extensions, generalizations. For instance, in the town problem that I was talking about, right? We showed that this, is equality ever achieved? I have no idea. I don't know. I don't know the answer to this. I thought about this for some time. I tried. As I told you, this was a question posed to me by one student. And I spent quite some time and I have no idea. What I managed to do was to show that if I take a regular pentagon and the sixth one at the center, you get this ratio to be somewhere around 1.9. And that's about the lowest I can do. In this kind of problem, I don't know if great mathematicians are spending time on these things, right? I mean, this is just something that was asked in a contest and some student asked this question. But no idea, right? Many such problems always suggest, sub-problems, new problems, which you cannot solve. But that's fine. I mean, that's really fine to me. And perhaps having a collection of problems that we can partially solve is very, very important for many of us. For me, certainly, I consider it important. So let me just mention that. So here is another one. Okay, I like tilings, so let me take something related to tilings. Okay, so lots of tilings again is one major area where lots of projects can be done, lots of things can be done, simple problems, hard problems, and so on. So what we call a domino is a 1/2 rectangle. This thing is called a domino. One very standard problem asks, right, if I take an 8x8 chess square, okay, 8x8 as usual, I'm lazy to draw, right? That means there are 64 squares. Now what I do is to knock off, this is a chessboard or a checkerboard if you like. I knock off the corner squares, I cut it off. Then I'll have 62 squares. cover them using 31 dominoes. Question is, can you? I give you 31 dominoes. Potentially, they can cover 62 squares. So now I take an 8x8 chessboard. Chessboard means what? It's going to be black and white, right? Alternate black and white. And now I chop off the corner squares and ask you, can you cover the 62 squares using 31 dominoes? Answer is no. Why? Because if I'm going to take an 8x8 chessboard and with alternating colors, if this is black, that guy must be black. If this is white, that must be white. So every domino covers exactly one black and one white square. So the number of covered white squares must be equal to the number of black squares, whereas in my board, I have the number of white and black are unequal. Done. Proof. Finished in 10 seconds. What did we use? We used an invariant. One nice invariant here. One more problem here, close to this, and this actually gives rise to a very nice question. I give you a 10 by 10 chessboard. I mean, we don't have chessboards which are 10 by 10, what's the problem, right? And I give you 1 by 4 dominoes. Tetraminos are things we can do a lot with. Okay, so here is a tetram, one particular. Okay. I give you 1 by 4 domino. Now I want to ask you, what is the situation here? There are 100 squares, and I have given you a 4 square domino. Can one tile? Can one cover? Same question. Now here, again, the clock is looking at me. So this is a very nice problem you can play around a lot with. Let me just give you the solution for this case and then offer you a problem which is a lot more challenging and exciting. What is that? So for this one, area is an invariant, right? Area is an invariant, but it's not a good invariant. You want some other invariant. One thing you can think of, there are lots of things you can think of. This is from Conway, by the way. Conway is the master of all these analysis of games. So Conway has this brilliant suggestion here. He says, okay, put some numbers, right? Suppose I can come up with some numbers, right? So put numbers on cells. Understand the idea? I take the 10 by 10 chessboard. I'm going to put some numbers, integers if you like, but some numbers, in such a way that if I take any 4 adjacent numbers, they sum up to 0, let's say, right? If I put any four adjacent ones, sum up to 0, but sum of all cells is not equal to 0, then you're done. If I can come up with a way, because what will happen if I actually cover it with 25 dominoes, right? Then the local sum for each of these is 0, so the total must be 0. But I have set up numbers in such a way that, yeah? So it must be, then it's impossible. He just leaves it at that. And with some trial and error you can try, and here is one that works. So for instance, 1, 1, 1, minus 3, 1, 1, 1, minus 3, 1, 1. I don't know if you can see. Maybe I can write. So here are 10 numbers, right? Consider the sequence of 10 numbers, right? Look at this. Wherever I place a 4-linked domino, what will happen? This will give me 0, this will give me 0, this will give me 0, so you can try. Okay? So, in general, so let me call this an, n equals 1 to 10. So the mnth cell mn, place value or write let me say m times an. This will do the job, because each row will generate a total sum. What is the sum here? 8 minus 6, 2, right? The row will give you 2, and so you know that this thing, if I tile using any dominoes at all, here it's not going to work. Another way of thinking about it formally is you could think of it as colors. You are using 3 colors, 1, minus 3, and 9, and you are coloring the advantage of something like this, and this is what he talks about as arithmetization, okay, or, you know, anything where you use numbers to solve the problem. And some, yeah, this is only for 1 by 4.
What about the other two cells, last 2 cells?
You can't. We are trying to prove that you cannot tile a 10 by 10 chessboard using a 1 by 4 domino, right? I'm saying in general, whenever you want to do a construction, you show the construction. You want to show that the construction is not possible, you have to find some invariant, right? And that heuristic that you learn has tremendous mathematical value, right? And you know, suddenly it liberates you from various ways of thinking. You know, it helps you generalize, specialize. I can give you lots of examples of this kind. But the point is that this preparation on the board is actually enough to tackle a very general problem. Given an A by B board, can one tile using A by B domino? All positive. What kind of conditions must be there? And I assure you that there is an answer, and it's a very beautiful answer. You can start thinking about it, and there is a lot you can do. In fact, Conway has exercises for higher dimensions as well, you know. But anyway, I don't want to go on. What I wanted to point out was that somewhere, you know, in all this hectic stuff that we have got, you know, this life that we have got, especially the life of the 15-year-old and the 17-year-old, somewhere time has to be found for this. If we cannot do this, right, the joy of whatever there is pleasure in mathematics is in solving problems of different kinds, and especially with the kind of richness in mathematical experience that we can give. Now, we need a collection of, you know, each of us needs a collection of 20, 50 problems of that kind. Problems that are not routine, but convey some of those values that I was talking about. Convey some of those processes that I was talking about. Especially for me, ever since I was involved in this National Curriculum Framework exercise, many times I've talked to teachers about the shifting of focus from content to process. So people ask, but then what are these processes? What are the illustrations of these? Problem solving is the domain of illustration of all these, in my opinion. Virtues of estimation, where you don't know the answer, but you estimate the answer. Where you don't know the answer, but you approximate the answer. That's very important where you don't know the answer, right? We need to create a whole lot of problems of that kind. And of course, my training being what it is, I'm talking about combinatorics, you know, elementary geometry, and things. No, you know, there are experts in calculus, there are experts in differential equations. I'm sure there are lots of such things where we can think of, where you want to solve the problem, but in the process of solving the problem, there are some very important mathematical values that you illustrate, you get trained in. And in my opinion, this kind of making conjectures, looking for counterexamples, looking for invariances, finding numerical invariants, the kind of exercises that we get out of those, right? The kind of richness of mathematical learning, doing one impossibility proof of any kind. I mean, I think it's really liberating of some kind to be able to do that. To come up with formulas, right? Come up with formulations, move between different abstractions, different kinds of representations. Now, we need a bag of tricks of that kind. Can we have a lot of problems? Yesterday I was talking about a project base, and I think we need a problem base as well, right? Without worrying about whether they are, you know, trigonometry problems or calculus problems or whatever, but some mathematical experience comes. And if every child has, not all of these, right, because interests are different, abilities are different, whatever, but if every child can be exposed to some aspects of these, you know, very rich thing, some experience of problem solving and finding the answer on one's own, or be guided using clues to find answers of this kind, I think the experience will be dramatically different, and we have to find some way of doing that. Thank you. Let me stop here. Sorry that we have.
Since there are more than one Conways, maybe John H. Conway.
This is John Conway, John H. Conway, very much. Well, in fact, I didn't know that there were more Conways. I'm sure there are in the world, but John Conway. Okay. Well, hopefully.
Ah, yes.
Okay. So,
That Conway is also John B. Conway.
oh, okay. It's my ignorance.